So let's look at what the result we got for a point charge. We showed that the potential for a point charge is kq over r plus a constant. This constant can be any value you want. So this is then the formula for the potential due to a point charge, kq over r plus a constant. Now here is where people can make a convention or make a convenient choice of a reference of potential. If you put r equal to infinity, then this gives you 0. So the potential is equal to V node. So V node is the value of the potential at infinity. So we're going to make a convenient choice. Let's set V node to be 0. This means that we're choosing the reference of potential where the potential is 0. We're choosing this reference of potential to be at infinity. So for this particular choice, then, we can say that the potential is just kq over r at a point in space. Remember that when we say the potential at a point in space is kq over r, we're still not really saying the potential at a point. We're getting the potential at a point minus the potential at infinity, which we took to be 0. So there's no such thing as potential at a point. You always have to get the potential difference between 2 points. So whenever people say the potential at a point is kq over r, actually, what they mean is that the potential at the point minus the potential at infinity is kq over r. And the potential at infinity is taken to be 0. So for this particular choice, that the potential at infinity is taken to be 0, the potential can be given as kq over r. And that means that the potential is symmetric. If you go anywhere, it's spherically symmetric. If you go to any around a point charge on this sphere of any radius, the potential has the same value. I put positive charges give potential values that are red in color, and the color gets weaker as you go far away because the value of r increases, the potential gets weaker. For instance, if you draw a sphere like this sphere around the point charge, the potential, say, at every point on the sphere is 100 volts, for instance. The potential on this sphere at every point is, say, 90 volts, and so on. So the equipotential surfaces for point charges are spheres. What about if the charge is negative? If the charge is negative, then the Q is negative, then the potential values are negative, and the potential is still 0 at infinity, but as you go away from the charge, the potential has negative values. I put the negative value represented by blue color. So the blue, whenever you have blue, it's negative, and it's more negative when the blue is darker. So for instance, this sphere, if you make a sphere with this radius, the potential everywhere on this sphere is minus 100 volts, for instance. The potential on this sphere is minus 90, and so on. So the equipotential surfaces for point charges are spheres. Now, we got how to get the potential at a point due to one charge. What if you have many charges in space? How would you get the total potential at point P? This is going to be the subject of the next video, and this will then finalize this long process that we've been seeking, how to find the potential for a certain charge distribution.